Okay, the conditional probability of an event B given an event A is denoted the probability of B. We have this bar, and then we have A. So that's the probability of B given A. And the probability of B given A is the probability that occurs the probability of B given A is the probability that B occurs under the assumption that A occurs. Okay? We read P parentheses B bar A as the probability of B given A. And here's how we find it. The probability of B given A equals the probability of A and B divided by the probability of A. Okay? This one's important. So let's look at example 1. Example 1, we have a chart. And this chart contains the number of men and women that are not high school graduates, that are high school graduates, that have some college with no degree, that have an associate's degree, that have a bachelor's degree, and an advanced degree. And these numbers are recorded in millions. Okay, so we've got men, we've got women. It'll take a minute to draw the table. Not a high school graduate. Okay, then we have high school graduate. Then we have some college, but no degree. That's what the ND stands for. Then we have an associate's degree. Then we have a bachelor's degree. And then we have an advanced degree. And that just means they have a master's or a PhD. Okay, the numbers are in millions. Oops. And I misspelled millions. I'm tired today. Okay. So the number of men that are not high school graduates is 14.0, and that's 14 million, okay, because it's denoted in millions. Women is 18.7. High school graduates that are men are 29.6. Those that are women are 31.9. Some college, 15.6 with no degree. So they took some colleges at local university, local junior college, but they didn't finish. They just went for a bit and didn't finish. Women is 17.5. An associate's degree is 7.2 men. Associate's degree for women is 9.6. The bachelor's degree for men is 17.5. Women is 19.2. And the advanced degree, men is 10.1. And women is 9.1. Okay, a person is selected at random. Okay, A says, what is the probability that the person is a man? Of course, you will need your calculator. Should have told myself that, shouldn't I? Okay, so we need to find the probability that the person selected is a man. So what are we going to do to find that? We got a couple of things we got to do first. Okay, so to find that probability, this is just kind of like you normally find in a probability. Okay, so the first thing we need to find is what? The total number of people in the survey or in the poll. Okay, so let's find that total number. We know this is in millions, which is fine. So I've got what, and they didn't tell us. So I've got 14 plus 13.7 plus 29.6 plus the 31.9. 15.6, 17.5, 7.2, 9.6, 17.5, plus 19.2, plus the 10.1, plus the 9.1. Okay? Uh-oh, okay. No, there is a 13.7. Oh, and I wrote 18 up there. Oh, yeah. This should be a 13. That is going to throw things off there. Some reason I wrote, no, that's a 13. If I can read my own writing. That's a 13. My apologies. When we add that up, what do we get for our total? And of course, you could put this in a list if you wanted to. It will give you the sum. I don't know. It's probably going to take you just as long to put it in a list as it would to put it in just to add them up. While some of you are adding that up, what's the other thing that we need to know? We're looking for what's the probability of selecting a man. And so we need to add up the total number of men that there were, right? So somebody add up the total number of men for me while we're doing that. And we just go across the row. We've got 14 plus 29.6 plus 15.6 plus 7.2 plus 17.5 plus 10.1. Okay, who's got the complete total for me?
168.
I'm getting 195. Check your check what you put in there. You could have done like me and typed in the wrong thing. Originally, when I did this problem, I got 195 for the total, 195 million. What about total men? Yes, 94 million. Good. So we're getting 94 million on the total for the men. Then our probability of choosing a man is going to be the total number of men, 94 million, divided by 195 million, the total that were there, which is going to give me we get 0.482. Yes. Okay. So pretty much, guys, what that's saying is this data is evenly split between males and females. You've got a 48% pretty much chance of drawing a man. So that means there's a 52% chance of drawing a woman. Okay, is what that's saying. B asks, what is the probability that the person is a high school graduate? Okay, well this time, at least we have the total already done, right? So we know my total of everybody that is there is 195 million. We know that one. Okay, so we need to know what is the probability that the person is a high school graduate? Okay, so we go back up to our chart. Okay, so the number of people that are a high school graduate, we need that. So we're just adding up 29.6 and 31.9, correct? Plus 31.9 is going to equal, what's that going to give me? 61.5. Okay, so the probability that the person selected is a high school graduate is going to be 61,500,000, or you can actually just put 61.5, that's fine. And you're dividing that by 195 million. And you can say 61.5 divided by 195, you will get the same percentage or the same decimal. And that should be, what did we get? 0.315. Okay. So out of the people surveyed, approximately 32% just are high school graduates. Okay. No college, no hours, no degrees. All right. C asked me, and I'm going to flip to the next page because I don't really have enough room right there. C says, what is the probability that a person is a woman given that the person is a high school graduate? Okay, so we're going to have to find a couple of things here. So here's what we have. We have what we're looking for. We want the probability that the person is a woman given that the person is a high school grad. Now, I write it like this so that we can fill in the formula and know what we're supposed to do first, okay? So, I know that the probability of B given A equals the probability of A and B all over the probability of A. So here's what that means for us. All you're doing is replacing B and A with woman and high school graduate, okay? So this is like B given A. So that means I have the probability of a high school grad and being a woman divided by the probability of a high school grad. Okay, so if you can put it in that formula, it's a little easier for you to see because then you just calculate those parts. So we have to calculate the probability of being a high school grad and a woman, okay? And then we have to calculate, we know what the probability of being a high school grad is, right? We just found that. We found that in B, right? Now, this means that we are looking for, and this makes life a lot easier. So we got to find the probability that you're a high school graduate and you're a woman. Well, we can pick that out from the chart, guys. If you look over here at your chart, if I'm a high school graduate and I'm a woman, how many of those were there? 31.9, right? Yeah, it was that simple. So this is 31.9 over the 195. That's my probability that I'm a high school graduate and a woman. And all over, what's the probability that I'm a high school graduate? Well, we added up. What's the probability that you're a high school graduate? 29.6 plus the 31.9, right? Which was the 61.5. Okay, thank you. 61.5 divided by the 195. Now, you put that in your calculator. You can, I would suggest putting them in parentheses. And you can do it all at one time. If you'll do parentheses 31.9 divided by 195, then close that parentheses. Hold on, let me, I'll find the camera. Y'all have it in there before I do that. If I put it in parentheses like that, the 31.9 divided by the 195, and then that is over, I divide that by the, was it 61.5, Missy? Is that what you told me? Okay. Divided by, put you a set of parentheses there. If you don't, can y'all see? Okay, yeah, not 2, 5. Okay. Did we get about 0.51? Is that what everybody's getting? And yes, that's what we should be getting. See, 0.1. See? There's the notes where it's right. See, right there. I should just read what I write, shouldn't I? Okay, and that will give me 0.519 is what I should be getting. You didn't need all that up there. That wasn't an or, that was an and. The rule is for or. We deal with a lot of and or in 1332 and talking about set theory, and it's not fun. That's where I'm getting that from. I need to. Okay, let's talk about the general rule, general multiplication rule. Okay. It says if I have the probability of A and B, that will equal the probability of A times the probability of B given A, or the probability of A and B equals the probability of B times the probability of A given B. These are important. Okay? Whenever you have the need for a formula chart for the test, which you will have your notes, but like when you take the final, this will be on there. This will be on the formula chart for the final. Okay? The point is not for you to memorize it. The point is for you to know when to use it. And as you saw, I used it incorrectly a while ago. Example 2. In a certain city, %70 of high school students graduate. And I'm here to tell you that is not a good graduation rate. Of those who graduate, 40% attend college. Okay, find the probability that a randomly selected high school student will attend college. Okay? So, here's what we're looking for. We're looking for the probability that a student will graduate and attend college. Okay? Now, we're going to set that up using one of those formulas up there at the top. Okay? So, and we have the probability of all of those, right? So this really equals the probability that a student graduates times the probability that a student goes to college given that they graduated. Okay? All right. So, what's the probability that a student graduated? No, graduated. 70. 70%. And then what's the probability that they went to college given that they graduated? 40. So we're saying 70% times 40%. Well, we can't do that in our calculator. Well, actually, your calculator probably can. But we got to change those percents to decimals first, right? Well, what is 70% as a decimal? 0.70, right? Drop the percent, move the decimal 2 places to the left. Then 40% is 0.40. Okay? So the probability that the student graduates and attends college is pretty much 28%, 0.28. The easiest way, honestly, guys, when you do these problems like this, lots of times the easiest way for you to do them is for you to reason through them. Because think about it, you got 100 kids you got 100 kids in the class. 70% of them graduate, so 70 kids graduate. And then you want 40% go to college. Well, what's 40% of 70? Well, 50% of 70 is 35 kids. So you're going to be somewhere less than 35, close to it. And that makes sense. That's about 28 kids, 0.28. 70 times 40%, or 70 times 0.4 is 28. Okay. I show you the formula because technically we're supposed to use the formula, but if you can reason through that without formula, you can. Okay? Two events are independent. Definition. Two events are independent if the occurrence of one does not affect the probability that the other event occurs. Yes. If two events are not independent, we say they are dependent. Okay? And then we have the multiplication rule. For independent events. And it is the probability of A and B equals the probability of A times the probability of B. Now you'll notice at the top we said the probability of A and B was the probability of B times the probability of A given B. Well, that's because they may not be independent events. Okay, an independent event is, what's the probability? You have two coins, and whether I get heads or whether I get tails on the first coin does not affect whether I get heads or tails on the second coin. Okay, those are two independent events. It doesn't affect what happens with the next event. Okay, it doesn't matter what I roll on that first die. I still have the same, like if I'm looking for a 6, I got a 1 in 6 chance on that first die. I got a 1 in 6 chance on that second die. Even if I do roll a 6 or don't roll a 6, it's still a 1 in 6 chance that I'm going to get a 6 on the second die. It doesn't matter what I roll. Those are independent events. Okay, now, yes, we can play into the factor of if they bump into each other, but that's a whole different, that's a physics problem. Okay, and wind resistant and all that good stuff. And the surface being flat. But that's completely different. Okay, so then we have this strange little chart because, here's the deal, guys. Just because two events, okay, does the occurrence, so they have this weird little chart they give us. Does the occurrence of one event prevent the other event from happening? They're trying to teach you the difference between independent and mutually exclusive. Okay? So, does the occurrence of one event prevent the other event from happening? If you answer yes, these are known as mutually exclusive. The events are mutually exclusive. Okay? If you say no, then we go, does the occurrence of one event change the probability that the other event occurs? If we say yes, then the events are neither exclusive nor independent. Maybe I should. If we say yes, then the events are neither exclusive nor independent. Actually, she's the third person today to tell me that my voice has put them to sleep in the last 24 hours. I gave a test in 1332 today, and I had 2 different students come up and tell me, I tried to watch those videos, and, I was like cramming last night, and, those put me to sleep. And I guess she's living proof right there. So, if you can't sleep at night, just turn on my stats videos there, and you'll doze right off. No. So, if the occurrence of one event does not change the probability of the next event that's going to happen, such as flipping the coins, whether I get a head or a tail doesn't affect whether the next coin makes a head or a tail. The events are independent. Guys, they give you this chart and I give you this chart because they probably will ask you if the following events are mutually exclusive, are they independent, or are they neither? Okay? Because they like to do that with the whole vocabulary and things like that. I'm figuring there's probably some homework where they ask you if the events are mutually exclusive or independent. Okay? Unfortunate for us, yes. But this is a little chart that helps you with that. Just follow the flow chart. Okay? So let's look at example 3. 2 dice are rolled. I like the counting section a lot better. We get more into gambling over there. It's a lot nicer, in my opinion. Much more applicable. 2 dice are rolled. Each comes up with a number between 1 and 6. Let A be the event that the number on the first die is even, and let B be the event that the number on the second die is 6. A. Explain why events A and B are independent. And they will probably give it to you in multiple choice form, where you click the correct circle. They'll go, okay, decide if they're independent. You say independent, and then they go explain why. And then you pick the answer they like, the outcome of one die does not influence the outcome on the other die. That's it. That's the answer to A. That's how they like it worded. B, I want to find the probability of A, the probability of B, and the probability of A and B. Okay? The first thing that I'm going to do is we're going to note that these events are independent. These events A and B are independent. So that means I can use my formula over here about the probability of A and B is going to equal what? Probability of A times the probability of B, correct? Is that the last one I wrote? Yeah. Okay. So let's find the probability of A. A is 2 dice are rolled. Let A be the event that the number on the first die is even. So how many possibilities do we have of an even number on a die? 3. 3 out of 6, correct? So the probability that I get an even number is 1/2. Those aren't bad. The probability of B, okay, is the event that the number on the second die is 6. Well, that's 1. I only got a 6 on one side, right? Is 1 out of 6. So that means I can now find the probability of A and B, which is the probability of A times the probability of B, since they are independent, okay, which is going to give me 1/2 times 1/6, which is 1/12. That's not real great, guys. So you're rolling some die, you're going to make a bet. Let's not bet on rolling an even number and a 6. Okay, over there on that second die. The part that throws you bad is rolling that 6 on that second die. You're not too bad on the even. I mean, you got 50-50 shot there. Okay, let's talk about sampling with and without replacement. Ooh, she's snoring good now. I will definitely have to watch the video and chop out, listen to the video and chop out my commentary. When sampling without replacement, if the sample size is less than 5% of the population, the sampled items may be treated as independent. Okay, so when sampling without replacement, if the sample size is less than 5% of the population, the sampled items may be treated as independent. And I'm thinking there was something, there was a homework question about that, I'm figuring. Okay, I did go through some homework examples. We have another chart, okay. Let's see if I have enough room, I think, for the chart. Oh yeah, I got this. So, we have, does the event involve and or at least. Okay. Now this is a 3-pronged. Okay. So we're going to go up here. And this one is going to say if it involves and, we ask ourselves, are the events independent? Okay? And this one kind of tells you which formula to use. You know, I threw several out there with the probability of A and B, and then we had the probability of A or B. This one tells you which one, this chart tells you which one to use when, okay? So, does the event involve A or at least? So, if it involves and, like the probability of A and B, we ask ourselves, are the events independent? Okay? They actually put this in a little box for you. Let me try to be a little more nicer here. If you say yes, they're independent, then we can simply use the probability of A and B is, whoops, we need a B, is going to equal the probability of A times the probability of B, like we did when we rolled the dice, okay? They were independent. If we say no, then I've now got to take out that given part. I've got to multiply times the given, okay? So that's going to give me the probability of A is going to, A and B, I'm sorry. Probability of A and B will equal the probability of A times the probability of B given A. Let's say they involve, your event involves the words at least. This has to do with if it's at least, it's 1 minus none. Okay? It's pretty much all it is. So, the probability of at least 1 equals 1 minus the probability of none. Okay? And then finally, the last one we have is or. Okay? And if it's an or statement, we ask ourselves, are the events mutually exclusive? And I'm going to abbreviate that. Are the events mutually exclusive? If we say yes, they are, then we have the probability of A or B is going to equal the probability of A plus the probability of B. And that's what we learned last time. And if we say no, they're not mutually exclusive, then we have the probability of A or B is going to equal the probability of A plus the probability of B minus the probability of A and B. Okay. So the first thing that you have to do is you have to determine, are they mutually exclusive, are they independent, are they neither? Okay, so that you kind of know what's going on there. And guys, if you look at this chart, when I'm using the word and, notice the and talks about them being independent or not independent. And if they're using the word or, then we talk about mutually exclusive. It's not like we talk about both independence and mutually exclusive with and with or. Okay, it appears from the chart that and correlates with independence and or correlates with being mutually exclusive. Okay, and from there you determine, guys, pretty much if they are independent, you can just go straight forward. You don't have any of the extra stuff in there. It's a multiply. Okay, if they're independent, we're just multiplying over there, we're good to go. If they're mutually exclusive, then we're adding. You don't have to take anything out of there. There's no crossover. Okay, I know that's a lot. There was a homework example that we had not done one like, and I picked out for you at that time. This was late at night one day. An unfair coin has probability .4 landing heads. Okay? Now, it should have what? 0.5, right? But this unfair coin has the probability of landing 0.4 landing heads. That means that what they've done, or what you can do, if you somehow grind off on that side of the head enough material, enough metal, that when it falls, that tail is heavier. So it's going to fall 0.6 or 60% more. It's heavier on that tail side, so it's going to fall down. That head's going to fall down. Heads is going to be up. Okay? An unfair coin is probably 0.4 landing heads. Well, actually, that would mean that the head was heavier if it only has 0.4 of landing. Don't worry about how to do that. The coin is tossed. Let's just toss the coin. I'm overcomplicating the problem. We'll cut that out too. The coin is tossed 7 times. We're going to come up with a 10-minute video here. The coin is tossed 7 times. What is the probability that it lands heads at least once? Okay? What is the probability that it lands heads at least once? Okay, so this is an at least once problem. So that means it's the middle of the chart. And the probability of at least once is 1 minus the probability of none, right? Okay, well, what's the probability of none? That means that it's going to land tails, right? Well, if it's 0.4 to land heads, what's the probability of tails? 0.6. Good. So I know I've got 1 minus that 0.6, but that 0.6 is the first time. Okay? What is it? How many times am I flipping it? 7. So that's 0.6 to the 7th power. That's the same thing as saying 1 minus 0.6 times 0.6 times 0.6 times 0.6 times 0.6. 7 times. Okay? I know I didn't say that 7 times, but 7 times, right? So you take your calculator. What is 1 minus 0.6 to the 7th? Do we know how to do the rooftop? That gives us the exponent. Everybody know how to use rooftop? We will do, let me find it. 1 minus 0.6, here's my rooftop, to the 7th. Okay, what do we get? Yeah. Okay. So I do get 0.972. So it's saying what is the probability that it lands heads at least one of those times? Okay. If you're betting, I'd bet there's a 97% chance that it's going to land heads at least one of those times. Okay. Let's see, do we want to, oh, that's a long little problem. we do need to do, these were just extra homework examples. We'll go ahead and we'll do 5.4. We'll go ahead.